Good evening, everyone. Welcome to class 6 of stochastic control and communication. So we'll do a little recap of what we saw last class. We saw about MDPs, Markov decision process, where you had a state space. So the example that we took in the last class, the state space was you had two states, S1 and S2. Then you had your action space. Action space, you could take three actions. Two actions when you're in state one, A11 and A12, and one action when you're in state two, A2. Right? Okay, so now there was transition probabilities. The transition probabilities were if you are in state one and you take action A11, right? Then you end up at state S1 with probability 0.5. Similarly, if you are in state one and you take action A11, then you end up in state S2 with probability 0.8. Similarly, the probability that you end up in state S1, given you're in S2, given you're in S1 and you take A12 is 0. The probability that you end up in S2, condition that you're at S1 and you take action A12 is 1. Similarly, uh, your transition probability that you end up at state S1, condition you are in S2 and you take action A21 because you can only take action A21 when you're in S2. This is 1. But probability of you being in S2, condition you are in S2 and you are in A2, yeah, this is. So these are your transition probabilities. Transition probabilities. And you see each of these transition probabilities, they add up to 1. So after taking an action, so for a fixed action across all states, the possibility adds up to 1, right? Because you have to end up in some state after you take it. Right. Similarly, you have your rewards. So rewards RT S1 A11 is 5. RT S1 A12 is 10. RT S2 A21 is -1. Right? So these are your rewards. So if you draw the transition diagram, it will look something like this. You have two states. State 1 is S1. State 2 is S2. Right? If you take A1, if you take the action A1, so I'll be drawing with three different things. Your black line is your action A11. Your blue line is your action A12. And your green line is action A1. First A1. If you take action A11, you can end up with a reward of 5 with probability 0.5. You end up at S1, you get a reward of 5 with probability 0.5. Okay. If you take action A12, then with probability 1, you end up in S2 with a reward of 10 and with probability 1. When you're in S2, if you take A21, you end up in S2 with probability 1 and with a reward of -1. So the first term in the bracket represents the reward that you get for taking that action in that state. The second term represents the probability, transition probability. Okay. So last class we saw about different types of decision rules. So first we saw was a deterministic Markov policy. Phi and D. So we fixed n equal to 2 for two epoch decision problem. So it's a two epoch decision problem. So here, what do I mean by two epoch decision problem is I'm looking at two steps decision. So I'll take decision two times. First time is to go from 0 to 1, and next time is go from 1 to 2. So the first epoch, I will call it as zero epoch. So at epoch 0. This is just an example of a Markov deterministic policy. So how do you define policy is it's a function which takes state and gives you an action. So what this means is under this current epoch 0 decision Markov determination, we take state S1. If you are at state S1, then you choose the action A11. And similarly, if you are at state S2, then you choose action A2. Right. And epoch 1 is if you're at state S1, you take the action A12. If you are at state S2, you take the action A21. Okay, so yeah, right now we are not talking anything about whether this is an optimal policy or not. We are just defining how do you mathematically represent the proxy. Next, we'll slowly come into how to find the optimal policy and so on. But first, we'll learn what are the different types of policies there are, and how do you mathematically represent those policies. So if you're writing on a deterministic Markov policy, then given a state, you'll get an action. You have to write down the function which maps states to the actions. Okay. The second one we saw was a randomized Markov policy or PyMR. So now since your policy is randomized, then the what you get instead of a mapping from state to action, what you get is a given a state, you get a probability distribution function over all the action space. Okay. So basically, similarly as a in the above policy, the deterministic Markov policy at epoch 0, now your randomized Markov policy, I'll define it as so Q gives you the probability distribution. So if you are at state S1 at 0th time instant, then you take the action A11 with probability 0.7. Right. Similarly, if you are at state S1 at time instant 0, then you take A12 with probability 0.3 because there are only two actions you can take when you are at S1. So this is your one of your probability distribution on S1. You have to do the same thing for S2. But for S2, since there is only one action, so you have to take that action. So A21, you have to take with probability 1. So these are the two probability distributions that you have mapped over. So given a state, you get a probability distribution over the set of actions. Right here, what happened was given a state, you get an action that is deterministic Markov policy. Here, you have given a state, you have a probability distribution over the actions. If you have just one action, then you have to take it to probability one. There is nothing you can do about it. And one important point here that we made an observation last time was, if you sum over all the actions that you can take at a fixed state st a, that will be one. So a belongs to all actions that you can take if you are at state st. So ast is the set of actions that are available to take if you are in state st. Okay. So this is an example of randomized Markov policy. So we still have to define at epoch one. Yeah, it could be anything. It could be the same thing. If it is the same thing at each and every time instance, then it's known as stationary um, Markov policy. But since we have not doing a stationary randomized Markov policy, we're doing just randomized Markov policy. So I'll write at epoch one. Right. Similarly, you write Q D0 MR S1 A11 is equal to 0.4. You can write anything. If you have written, if you have written the same probability distribution here also, then it would have been stationary. So it would have been also stationary. So it would have been stationary randomized Markov policy, but we are not doing stationary right now. So yeah, QD0 MR S1 A21, and from this definition here, you have to fill this with 0.6, and again from this definition, um, if you're at state S2, then you can only take action A to 1. So this is 1. And yeah, this is a patient decision. Now, we also had history dependent policies. And for this particular example, I'll call this example 1. For this particular example, your space of distribution process is equal to your Markov decision process. So we will introduce a new action here so that you have something else going on, which can which will separate you from the history decision policies and your Markov decision policies. So I'll again introduce another MDP. So basically, when I mean I'm defining an MDP, I need to define all these parameters that I've just defined. So I need to define the state. I need to define the action space. I need to define the transition probability matrix. I need to define the rewards. And then using all this, I'll be able to draw the transition diagram. If I'm able to do all this, then I have mathematically modeled an MDP. Okay. I've not come up with an optimal solution of what action should I play at each and every time. I've just come up with the model of the MDP. So again, I'm defining a state space S as S1 and S2. A belongs to, you have three actions, you have four actions now. A11, A12, and A13. You can take three actions when you're at state 1, and you can take only A21 when you're at state 1. Okay. So probability transition matrix, again I'll define. So probability you are at S1, condition that you were at S1 and you have taken the action A11 is equal to 0.5. Probability that you are at S2, given that you were at S1 and you have taken A11 is also 0.5. Okay. Similarly, you are at S1, given you are at S1, but you have taken the action A1 to is 0. Probability of S1 is you are at S2, given you were at S1 is 1. Now state 1 has one more other action, which is A13. So probability that you were at S1 conditioned on you were at S1 and you have taken A13 is 1. Probability that you are at S2, given that you were at S1 and you have taken the action A13 is 0. So this is the opposite of this. And the last one is if you are in S2 is 0. And probability that you are at S2. So I just to make everything clear, I'll write this down again. This is your state space. This is your action space. These are your transition probabilities. Okay. And then your rewards remain the same, but you have to add a reward. So I'll write down the rewards once again. The rewards were reward S1 A11 is 5. Reward S2 A21 equal to -1. S2 A12 is 10. S1 A11 is also 5. Reward S1 A13 is 0. Okay. So we want to write a deterministic history dependent policy. So first we want to write a deterministic history dependent policy by HB. So the N is still 2. So I'm taking patients at two epochs. So at decision epoch 0, I have D1 HD S1. So if I have at state S1, because there is no history now, I'm at point 0. There is nothing back other than me giving you which state you are at. So you just take the decision based on which state you are at, right? But at decision epoch 1, what happens is you get to add a table. The table is what did you do at decision epoch 0? So what were the state action pair? And what is your state at decision epoch 1, right? So you can be at S1, you can be at S2. If you're at S1, you take a decision. If you're at S2, you take a decision. So suppose your S0, A0, this pair is what you are writing down here, is S1 and A11. So what does this mean is you were at state S1 and you have taken the action A11 in the previous epoch. You could also be at state S1, take A12, You could also be at S1 and take A13. Oh, I didn't have a transition diagram. Okay, that's good. So you could be at state S2 and you can take the action A21, right? So if you're in state S1, take the action A11, then you can end up in state S1 with probability 0.5, you can end up in state S2 with probability 0.5. So suppose you ended up in state S1, then one policy is you take action A13. If you ended up in state S2, then you have to take A21 because there is no other action possible that you can take in state S2. Similarly, S1, A12, if you are additionally if you were at S1, you have taken A12, then there is no way you could have been in S1 because the probability 0.1 you would have gone to S2. So this is infeasible. This is A21. Okay. Next, yeah, suppose in the previous epoch you were at S1 and you are taking the action A13, then you would have been in A11. This is infeasible because the probability of going to S2 if you are in S1 and you have taken the action A13 is 0. Similarly, for the last one, this is infeasible. Here you take the action. So you make a table yourself. Depending on the history, you take an action. If this string of history is not possible, then you will have no action to take because that string of history is not possible. Right. Okay. Similarly, you have randomized history dependent policy files. So at decision epoch 0, so at decision epoch 0, now because you are writing down the randomized history dependent policy, you would again give a probability distribution function given what state you are among all the actions. So here I would refer to this as B0 HR S1, A11. So what this means is if you're at state S1 and if you're taking this randomized history dependent policy, then you take action A11 with probability 0.6. If you're at state S1, you can also take A12. You take action A12 with probability 0.3. If you're at state S1, you can also take A13 when you take A13 action with point. Right. Here again, you get the same equation. So Q DO HR S A for all A belongs to AS. This is equal to 1. Okay. Now, if you are at state S2, then there is only one possible action that you can take, that is A21, and you take that to probability 1. This is a decision epoch 0. Now, for decision epoch 1, again, you make a table in the same way you have made a table for deterministic history dependent policy, but instead of what actions you are you have, you are going to make a table on probability distributions. So how do you do that is you have your history, that is decision epoch 0. Then your decision epoch 1. And then in the decision epoch 1, you can have S1, you can have S2. It can be in any one of the states. If you are in S1, you can take three actions: A11, A12, A13. And if you're in S2, you can take only A2. Right. So this is basically S0, A0. This could be S1, A11, similar to similar way that we have written by the data mystic. This is your history basically. S1, A12, S1, A13, S2, A21. So you can write up some distributions, but just make sure that your policies, the probability should add up to 1. But here, if you are a test 2, then you can take only one action, so it should be 1. So if you're a test 1 intake, then this whole things become infeasible. This is 1. This becomes infeasible. This is 0.2, 0.1, 0.7, something, which adds to 1. Here, again, this becomes infeasible. This is So if you take a policy based on your history, here you take the policy based on this probability distribution that we have written on this, then basically you're taking randomized history dependent policies. So these are basically the different types of policies that we have. So one is the deterministic Markov policy, randomized Markov policy, history-dependent policies, deterministic history dependent, randomized history. And then there's one more thing where you have stationary uh, policies, but then history dependent, you can't have a stationary policy because at each time epoch you can have different strings of histories. So stationary policies are a part of Markov computation processes. So there at each time instance you can have the same decision policy. Then it's known as stationary policy. So till now, what we have seen is we have seen policies of different kinds. Right. We have seen Markov dependent Markov policies, deterministic Markov policies, randomized Markov policies. We have seen history dependent policies, deterministic history dependent policies, randomized history dependent policies, and so on. So now we'll ask the how to solve or how to obtain the optimal policy. So what we want is pi, which is your policy, which is a string of functions which belongs to some, for now we'll say Markov deterministic policies, such that they minimize your total cost. So if we just go back and remember what we had was we had a terminal cost plus stage-wise cost. So this is your terminal cost. This is your stage-wise cost. And if you remember this stage-wise cost, you had the dynamics here where you have current state, you have current action, and you have a randomness in the WK. Then you have the evolution as f of xk comma uk comma n. You had this. And why is this a function of x0? Because your trajectories would depend on your initial state, right? So basically, what we want to find is we want to find, and here this whole trajectory is calculated based on your policy pi that you have given. So UK selection, the selection of UKs is done by the policy pi. So basically, this is your average cost that you see if you take or follow policy pi. Pi is some policy that is fixed. So what you want is you want the optimal policy. So optimal policy would have an optimal cost, and that cost is given by so in the space of all Markov deterministic policies, you want to find the policy which optimizes or minimizes the total cost that you have done. And pi star, I'll call it the arc min j pi x0. And this pi star, I'll call it the optimal policy in Markov deterministic policies. This is what I want to find. Okay. So first we'll see how computationally how hard it is to note down all the possible policies in Markov decisions. So suppose the cardinality of a state space is B, which is a finite term. So this cardinality means this is your size of state space. Cardinality of your action space is A. This is your number of actions at each time step, or you can also call it as a distributor. Okay. N is your time horizon. So now the question that we are interested in is what is the size of Markov decision policies? So what is the size of the set of what is the size of this pi MD? How many policies are there? Right. So we want to find the cardinality of pi MD. First, we'll look at it for a single time step. Uh, so I'm not writing this down initially. First, I'm writing down number of decisions at each time instant is basically a power. Because we have a choices, that is your action space, for each state, and there are b states. So you you have a power b different policies that you can make for a single time. But since there is n time instances, so you basically get the total number of decisions possible is a power b whole power n, which is a power b equal. So this is if you're just looking at Markov decision process. So this is a huge number of policies that you need to search among. Right? If you're looking at, I'm denoting this with J double star. This J double star is if you're looking at all the policies in history dependent policies, right? And this remains the same. This is J pi x0 expectation Gn xn n minus 1. Now your action depends on the history, whole history that you have with you till that point k. Then here your hk is your history at time k, and you know that history, whole history, that is x0, mu0, the strategy that you have applied at 0, x1, mu1, and so on. Okay. So yeah, these things remain same. That is your uh, state space is b length, which is finite. Your action space is of a length, which is finite. Your n is your time horizon. Phi hd is equal to how much? So here it depends on which time step you are. If n equal to 2, you have decision rule 0 and decision rule at 1, right? And each time you get a power b in the same way. This is ab, but in the second time instance, you get ab whole square, right? This is for n equal to 2. This is for n equal to 1. This is for n equal to 2. And similarly for n equal to 3, you get ab, a, ab square, a square b cube. Because each time you're adding us with the history, you're adding a state and an action pair with you there. So those many number of choices would increase, right? So whatever the class of policies you choose, ND, RD, HD, whatever it is, the search space for all the policies is too expensive, and then to write down all those policies and then compute J star for each of them, and then um, find the optimal policy is a very hectic task. It's going computationally very taxing. So what you do is we 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 depend on the structure of cost function to come up with a algo to give us the optimal policy. Okay. So what? So two main things is cost is added at each step. So you take an action and then combined with some noise, you get a it tells you the cost and the next state that you're in. Okay, so cost is added at each step. It is a stepwise thing which occurs, or a sequence of decision making which occurs where you at each decision making that you have done, you get the feedback of what cost you have incurred till now. Right. And the structure of the cost function such that because you have this additive structure where you get a cost and then you add it to it, you get a cost and then you add it to it, and then there is this notion of terminal state and terminal cost. So I'll write down the cost function again. This is for any pi. Pi need not be in MDH, it could be for any pi. Your cost function is the average terminal cost plus your stage wise costs, where your mu k is basically function of wk, function of xk, where you get the uk. Okay. So what we want to find is we want to find j star x0. This is set of all policies that whichever you could choose, it is MD or AD. It's j pi x0, and you have your underlying dynamics where your trajectories follow fxk plus 1, fxk, mu k, w. Okay. So before going into all this, we'll maybe in the next class we'll learn about principle of optimality. So principle of optimality. If we go into principle of optimality, what we do is uh, we write we discuss a different type of problem which is known as the shortest path problem. So this I'll discuss in the next class also, but just to see what we're trying to do here is, so suppose I have a state A, I have a state B, right? To go from state A to state B, I can go through this path where I have three intermediate nodes, right? Similarly, I can go from A to B in this path. Similarly, I can go from A to B in this path, and I can go from A to B this path, right? So basically, suppose you open your Google Maps and you see that you want to go from this location A to location B, it will give you multiple paths options to go from. So this is basically like that. But then instead of just giving you the straight path, what we are doing is we are breaking up the problem into small chunks and uh, showing that okay, to go from A to B, you go from A to some intermediary node, say C or D, and then from C you go to D. So it's basically like saying that okay, you have to go from here to some place B, then you first go straight, and then you turn left here, and then you turn right, and maybe some other parts takes you the first left and right is the same, but after that there is a you can split into two ways. You can take a left and again you can come back to the same path, and you can take a right also and you can come back to the same. Now these shortest path problems are pretty similar to your stochastic control problem. Stochastic control problems, right? Because the cost of travel. So what is the cost of travel that you see is basically you can look it as distance. You can maybe while going from A to B in your mind you're trying to minimize uh, distance that you want to travel, right? So basically what you'll do is you look at all the individual distances of these. Right. If you have distances of these, then if you want, you can just calculate the distance that this path by adding up all the distances. Right. You can add up all these distances, you can add up all these distances, and you can find the total distance that you're traveling. Similarly, you can also do it by minimizing time. So instead of distance, there is some time associated with each path. So each path takes you some amount of time to go through. And here also it takes some amount of time. Here also. So if you want to know the total time taken to go from A to B, if you follow one path, then you can just add up those times. So basically the cost function that you're trying to minimize in the shortest path problem, either be distance or time, is basically adding up your stage-wise costs, which is same as, so you add up stage-wise cost, right? So this is what you see in your stochastic process also, because your cost function J pi looks like summation of jk, xk, μk, wk, where these are your stage-wise costs. So you take an action and then you add the cost for the action that you have taken. So you want to go, you have three choices here. If you choose this action, then you go here, and based on this action, you get that amount of time here. Then you say, okay, if you're here, then you have only one action to do. Now, if you're here, then you can choose this or this. If you choose this action, then you add up the time. So that is pretty similar. So basically, one similar is the adding up, and yeah. So the similarity is cost you incur is added up at each state, each stage, right? So basically, your stochastic control problem is a generalization to your. So it's the shortest path problem. If you generalize it, then you get the stochastic control. Anywhere the stochastic control point. So, okay, let me uh, give you a brief idea of what principle of optimality is. The principle of optimality, I'll not write on the theorem right now, says that if suppose this is your optimal path. So this red thing, this is your optimal path. Okay. And let me call this node as C. So if this is your optimal path, now I change the problem to optimal path for what? For from A to B, you have your optimal path as this. Now if I change the problem and say that, okay, I want the optimal path from C to B, then in that case, this should, sorry, the optimal path from C to B also should be this. It can't be this, because if this is your optimal path from C to B, then this can't be your optimal path from A to B. This observation is what we'll be actually using to claim to write down the principle of optimality. So this is your optimal path. If you know your optimal path, then your sub problem optimal path also would be the sub part of your optimal path for total um, total number of decision points, right? Because if this is your optimal path for the sub problem, then you all have a better path or better policies that you can choose. Yeah. So this is your principle of optimality. Okay. So this we'll discuss in the next lecture, next class, and also we'll discuss about dynamic programming. We'll do a proof of optimality for dynamic programming. We'll discuss principle of optimality. Basically, it is the idea is this: if you have the optimal path, then your sub problems would also have the same suboptimal, like truncated optimal paths. Then using that, we'll do a dynamic programming where you go stage wise from the back. It's not basically stage wise; you do it in a recursive manner. Then we'll have proof of optimality with that. I'll stop recording.